Okay, good morning everybody. Thanks for coming back that early. So today it's my pleasure to have Zubin here. He has got his B.Sc. M.Sc in Germany in the Jacobs University. Moved then on to do his Ph.D. With Harald Haas in Edinburgh University, where he finished in 2007 actually a thesis on femtocells, which 2010. I think. Sorry?
2010.
Oh, 2010. Okay, you started in 2007. Okay. Voilà, so we have a professional here on femtocells, and I hope we're going to have a great insight today on various important industrial issues related to femtocell rollout, which is interference. Thank you, Zubin.
Okay, thanks a lot, Misha. First of all, can everyone hear me? Yes, I guess. Okay, good. Before I start, all right, I hope that's better. So before I start, let's see how many people will find this presentation boring. So how many of you are here from industry? Just put your hands up. No one? And from academia? Okay, good. So do the letters PD, CCH mean anything to anyone? No? Okay. So I have my work cut out for me then. Okay. Thanks for the introduction. I work for a small research lab in Munich, which is a subsidiary of a very large operator in Japan called entity DOCOMO. We are DOCOMO Euro-Labs, and we have about 50 researchers. I'll be talking today on LTE and LTE-Advanced interference coordination for femtocells. And since it's so early in the morning, you'll be happy to know there's not much mathematics. Yeah, so let me get started. But before I do, I want to thank Sekan, who is right here, for providing me with some of the slides, and also another colleague in Japan whose name is Nobuhiko Miki. Okay, so I've tried to make the presentation as interesting and lively as possible, so I hope you guys don't fall asleep. And I've roughly divided it into three parts. So in the first part, we will refresh our memory, or help you understand what LTE and LTE Advanced is about. And we'll have a look at some of the already existing IC inter-cell interference coordination techniques that are available in LTE. And once we've covered that, we can actually get into some more details. So the second part of my presentation will be about femto-to-macro interference. So this is a major issue because femtocells are assumed to be closed access, and if they're closed access, what happens when you have a friend coming to your apartment and still wanting to have his cell phone working, but he can't connect to your femtocells? He's going to see very high interference from your femtocell. So how do we address this issue? So this is quite a major issue, and what we'll do is we'll look at some techniques that are already discussed in 3GPP in 2009, 2010, and then what we'll do is we'll only look at the control channel, and furthermore we will try to analyze how we can improve the performance for the control channel. And then part 3 will be femto-to-femto interference, which is actually Sekan's PhD topic. We will look at the effects of network densification. This is a word that's being used more and more these days. And then we look at two different ways of addressing this problem. One, a centralized approach, and the other, a distributed approach. And then we'll draw our conclusions from our discussion today. Okay, so part 1, know your LTE A, B, and C's. Okay, so what's this whole LTE thing about? So I'm sure most of you already know this, but let me go over it anyway. Evolution. So LTE is basically the reuse of 3G spectrum, but it's an evolution. It's a completely new technology. As you know, it's based on OFDM. And it promises to bring much higher speeds. and also by using the old spectrum, it should be a smooth introduction or smooth rollover to fourth generation and fifth generation systems. So if we look at this graph, we see on the x-axis time in years, and we see the system performance on the y-axis. And if we start in the early 2000s when 3G was first introduced, we had a relatively low requirement for system performance, but as we are all carrying these devices these days, watching YouTube videos, the demand for system performance has been increasing and increasing. And so WCDMA evolved into HSDPA and HSUPA. In Japan, WCDMA was under the former name, then we had high speed, and now we're somewhere over here where we have LTE. And this symbol here is called CROSSY in Japan. It's an LTE release from DOCOMO. And up to this point, we've been using 5 to 20 megahertz of bandwidth. But as the requirement for system performance increases even more, we'll obviously need more bandwidth. So this is one way of countering the problem. And that's in the realm then of LTE-Advanced. And this will be operating in 5 times the bandwidth, so 100 megahertz. And of course, the other way of countering the problem is by introducing more nodes in the network, and that's why we are here today. Okay, so bandwidth of 1 megahertz, peak throughput of 1 gigabit per second. These are all lofty standards. And furthermore, as if that wasn't enough, it has to be backward compatible to LTE, and it should meet or exceed the IMT advanced requirements. So we've all got our work cut out for us, and all the work we're doing is going towards the proper functioning of LTE Advanced. Okay, so I've mentioned this word, or these two words, backward compatible. It's very important in LTE that new systems should be able to perform with old systems, and furthermore, old systems should be able to perform in new systems. So I like to look at it as this bullseye problem. So basically, LTE Advanced should be an evolution of LTE with new bands which are available, but it should at the same time be backwards compatible. And furthermore, a user equipment in an LTE cell should be able to work in an LTE-A cell, and the other way around. So release 8 is the red circle, but is encompassed by release 9, which is encompassed in turn by release 10. So with all the new technologies that release 10 comes with, release 8 terminal should still be able to function in it. So this is the reason I'm mentioning this, is because a short while ago in 3GPP, it was very important that whatever techniques we develop for interference coordination should be backwards compatible. Okay, and then I just want to point out the difference between LTE and LTE Advanced in terms of requirements. So you can have a look at all the numbers in this table, but the general trend is that LTE Advanced is 1.4 to 1.7 times the requirements of LTE, and we have to basically try to work towards that. So from 300 megabits per second peak throughput to 1 gigabit in the downlink, similarly something like that in the uplink, but a bit reduced. And yes, so we have advanced MIMO techniques and such things to bring this about. But also femtocells will play a major role in that. Okay, so what's new in LTE Advanced? So I mentioned this thing about bandwidth. So here are some of the key technologies that we'll be dealing with in LTE Advanced. First one is wider bandwidth, and they do that by carrier aggregation. So they don't just simply expand the bandwidth. What they do is they have component carriers, and they just use many of them. So LTE works with one component carrier up to 20 megahertz, so you could think of it as this bit over here. And in LTE-Advanced, you just have many of them and you put them together and that's your system. So it meets the ITU-R requirement for bandwidth, which was specified as more than 40 megahertz. This is 100 megahertz. And carrier aggregation is based on the component carrier concept to maintain backward compatibility. So for example, you could have an LTE-Advanced system working with 5 component carriers, and you could have an LTE system working on just one of those component carriers. So it's all working at the same time. Well, another thing is advanced MIMO techniques. This was covered very well yesterday in the first talk, so I don't want to go into it. But basically, MIMO will help to improve peak data rate, of course meet the ITU-R requirements for downlink cell spectrum efficiency. We have, as we learned yesterday, 8 layers in the downlink, 4 layers in the uplink, and we also have multi-user MIMO capabilities with enhanced CSI feedback. What else? We have enhanced IC-IC, so we have more functionalities to deal with inter-cell interference coordination. So what does that bring about? I don't think I need to tell you this, but it improves the user throughput, particularly at the cell edge, which is very important in LTE. It also improves downlink flexibility. The interference coordination for layered cell deployment with different transmit power levels. This is what we deal with. So we don't have a homogeneous network anymore. We have a heterogeneous network, which means that we have high power cells and we have low power cells embedded within them. And the analysis of interference gets quite complex when you imagine that the low power nodes are just distributed randomly in the network. It's not so planned as the high power nodes. So we have carrier aggregation, which we already spoke about, and this can be used to bring about some kind of interference coordination, as I'll show you later. And we can also do time domain coordination. So we can do frequency domain coordination where we partition the available frequency, or we can also do time domain coordination. And furthermore, we can enhance all of this by using power control. So that is enhanced IC-IC. We'll talk about that later. So this one is marked in red. And then we have relaying in LTE Advanced. So it improves the coverage, of course, because you have relays to forward the information. But at the same time, it's cost effective. That's because relays are not very complex hardware devices. They're just basically forwarding the data, and most of the processing is done at the base station. So there's either a wired link or a wireless link. And then, of course, we have COMP, coordinated multipoint transmission and reception. But I won't go into this because I'm not going to talk about that today. Okay. So, heterogeneous networks. Yeah, it's not a typo. I just want it to be funny. Anyway, why do we have these heterogeneous networks? So, 4G systems will be characterized by a very dense deployment of low power nodes. We know this. And it is essential that these nodes should operate without negatively affecting the overall performance of the system. So we can think of users connected to the macro cell as high priority users, and then users connected to these low power nodes as somewhat low priority users. So the high priority users should not experience a degradation in performance. So let's look at some of these. We have a relay over here which extends the normal coverage of the macro cell, and it could have a wireless backhaul to the macro cell. Relays will be open access because they should appear as macro cells to the users, and they are operator deployed, which means they can be planned, their locations. What are the 8 major issues? We have effective backhaul design, and we should mitigate relay to macro cell interference. But we won't talk about relays today. Let's move on to picocells then. Picocells have a wired backhaul to the macro cell. again, they're open access. Picocells are typically deployed in areas like airports, shopping malls, places where you have a large gathering of the public. And of course, they're also operator deployed. So the operator can decide where in the network topology they should appear. And relays help to, picocells help to offload traffic from the macro cell. That's one thing. And it's important in the case of the picocell to mitigate the interference they cause to the macro cell. This is exactly the opposite case now for the femtocell. So this is the focus of what I'm going to talk about today. Femtocells are an entirely different beast. This is because they're closed access and they're deployed by the users. So there's no planning, and the user decides who should access them and who shouldn't. So what happens when someone who has no access to it is in the vicinity of one? So that's what we'll talk about today, and we'll also talk about what happens when you have in the future a very dense deployment of femtocells. How do you reduce the interference one femtocell causes to another, because they're all closed access? Okay, so that is what we'll talk about today. Alright, now that we have established all this, why do we need interference management? So let's look at all the different interference scenarios we could have. I'm sure most of you know all this. So we could have femto user equipment to macro E node B interference, but if the femtocell is far away from the macro E node B, this shouldn't be much of a problem. Over here we have macro UE to home E node B problem. So home E node B is the femtocell using the 3GPP nomenclature. This is an interference that appears in the uplink, which is also very important, but we will not discuss this today. I have done some research on this, but it's out of the scope of today's discussion. And then we have, of course, the macro E node B to the femto UE problem, but we assume that the macro cell has priority. So for now, this shouldn't be a problem. This shouldn't be a problem that we'll discuss. What we'll discuss is problem B, which is the home E node B to macro user interference. Okay, so let's just have another overview of ICIC in LTE and LTE Advanced. In LTE, we have only one component carrier. So we have either bandwidth ranging from 1.4 megahertz all the way up to 20 megahertz, but it's always contiguous and it's in one component carrier. So you make do with what you have, and you try to come up with some interference mitigation techniques which can only work with this frequency reuse of 1. You can partition resources in the data channel, but what do you do about the control channel? So these are the issues we'll discuss today. You can do frequency domain ICIC, you can do time domain ICIC, but you're limited very much by the fact that you have one component carrier. On the other hand, LTE Advanced, you have a lot more flexibility. You have many component carriers. So you could possibly assign one set of component carriers to your macro cell, one to your femtocell, and completely orthogonalize the system. You could do frequency domain ICIC over multiple component carriers, time domain ICIC over one or many. So you have a much greater flexibility for interference management. But of course, if you want to have a backward compatible scheme, the lowest common denominator is what you have with LTE, not LTE Advanced. So I'll bring up another very commonly used technique, which is fractional frequency reuse. Again, all of you are experts, so you know this. At the cell edge, if you have a system where frequency reuse is 1, so all the cells use the same bandwidth, then the cell edge performance degrades quite considerably. But in LTE, one of the key performance parameters is cell edge performance. So what you can do is you can do fractional frequency reuse, whereby you reserve a certain set of resources for use within the cell center. So these white ones over here are used in the cell center, and then you have another set of resources which ranges from here to around here, where you distribute them among the different cells for use only at the cell edge. By doing so, you can still maintain a good performance for your cell edge users. And in LTE Advanced, you have a very nice functionality whereby all the cells are connected by a logical interface known as the X2 interface, and what they can do is they can exchange what is known as the RNTP, or the relative narrowband transmit power, between each other. And what it says is that one cell will tell another cell which resources he is using high power on. So for example, this cell over here will tell all the other cells that he's using high power on the last resource, and by doing so the other cells know that they should not schedule cell edge UEs on this resource. How is this done? This is simply done by transmitting a bitmap, so zeros and ones corresponding to the resources where high power is used. So it's very simple. In LTE, they don't specify in the standard any particular technique that you should use for IC. All that is specified are these these signals that are exchanged, and what the operator wants to do with these signals is up to them. Okay, so in release 10, what can we do? As I already mentioned, that we can do frequency domain IC and we can do time domain IC. We can have what are called protected resources, and we can have non-protected resources. And the lower power nodes must do everything they can to not cause interference to the protected resources, and the high power nodes need not do anything. So for example, in the frequency domain, imagine that the blue squares correspond to the macro layer and the yellow ones to the femto layer. So the femto layer could simply not transmit on a particular carrier and thereby not cause interference, and then these ones could be used for the very vulnerable UEs. So UEs at the cell edge, or for example UEs which lie within a femtocell. You could apply the same concept in the time domain. So here you work with only one carrier, for example, and for a particular fraction of the time the femtocell suppresses transmission. But then of course you can imagine, for example in this case where you have a two carrier system, the femtocell loses half its capacity. Also in the time domain it loses half its capacity. So this is not a very clever solution, but it's a solution that's actually very actively discussed in 3GPP. Okay, so now we could look at frequency domain IC. So in LTE, as we will discuss later, you have a certain subframe structure in the physical layer, and there are many subframes that form one frame, and there are many frames that form a superframe. But basically each subframe is divided into a control region and a data region, and the control region has to come before the data region because it contains all the information of how to decode the data. So on the femto layer, in any layer, the control region spans the entire bandwidth, and this you cannot do anything about this in LTE. So what you could do in the femto layer is you could schedule UEs on a particular part of the frequency resources and leave the other resources free. By doing so, you will cause less interference to this part in the macro layer, but you'll still be causing interference here. But the question is, that's all fine. This is called resource partitioning. It's very easy to imagine that this would work. But what happens to the control channel? there's full interference from the control channel from the femto layer to the macro layer, and you cannot do anything about that. So this is where the research that we've been doing comes in, and I will go over that in part 2. And then we can have, when we have multiple component carriers, the situation improves slightly. So on the femto layer, you could be using, for example, 2 control component carriers, and also on the macro layer. And what you have in LTE-Advanced is this nice feature where you have cross-carrier scheduling, which means that you use the control region in only one component carrier to schedule resources across both the component carriers, which means this part in the femto layer is blank. In the macro layer, you could actually use this control region to schedule resources across both the component carriers. By doing this, you have no interference to the control region of the macro layer, and at the same time, you also protect a certain part of the data resources, which you could then schedule the vulnerable UEs on. The only thing is that you need to transmit some additional bits to indicate which component carrier is doing all the scheduling. But this is provided in the standards. So this is something you could do with LTE-Advanced. And then, as I've already mentioned, you have time domain ICIC. In the 3GPP community, this is known as almost blank subframes, or ABS. And it's very simple. You just blank a certain set of the subframes in the time domain, and these subframes are then protected on the macro layer. But then there's an issue. Basically, in LTE, you measure the channel state information, and you transmit this information to the E node B, which then uses it to do scheduling, providing the correct modulation scheme, etc. So when you have this almost blank subframe situation, you could have across, when you're measuring the channel here, you'll have a very bad channel because there's high interference. But then in the next subframe, because there's no interference, you'll have a very good channel state information, and then bad and good again. So this would probably confuse the system and not result in very good scheduling decisions. So this, even though is a very simple scheme, it still needs some work to sort out these issues of channel state information. So this work is still ongoing in 3GPP. Okay, what else can you do? As you learned yesterday, we have these cell-specific reference symbols across the entire subframe. So you still have interference caused to these, and when you have that, if you lose the reference symbol, then you lose basically the entire subframe. So something needs to be done about that. You could possibly do almost blank subframes, but with non-zero transmit power, so really reduce the power but not completely. You could cancel the CRS interference at the user equipment. You could do some kind of transmitter side processing, etc., etc. So there's still a lot open to research. So it's not closed at all. Okay, so that was part 1, which should have given you a good enough background as to what can already be done in LTE without touching the standards at all. Now we move on to part 2, where we will compare some state-of-the-art techniques and furthermore show how to protect one of the most important control channels so that the system can still work. Okay, but before I do that, I have to show you this figure, because you need to know how things are distributed in it. So this is the physical layer frame structure in LTE, the almighty grid. It contains 14 OFDM symbols in the time domain and 12 subcarriers in the frequency domain. The subcarriers are spaced at 15 kilohertz, and this whole subframe is 1 millisecond long. Okay, so the first part of the subframe is the control region. The second part is the data region. The control region obviously should be smaller than the data region, otherwise you'll have a very high signaling control overhead in the network. The control region is not fixed in length. It can vary between 1 and 3 OFDM symbols in length. So that means that if you're scheduling very few UEs in your system, you need not use 2 or 3 OFDM symbols. You can even get by with just 1. But if you're scheduling a lot, then you could use the entire width. These black boxes, these are the reference symbols for one antenna port, as we saw yesterday. And of course, if you have more antenna ports, then you have more of these reference symbols. Okay, let's get into some further details now. There are 3 control channels. The first one is the PC Fitch. It stands for Physical Control Format Indicator Channel, and basically it tells the UE, this is all in the downlink, so the E node B tells the UE how long the control region is going to be. It's either 1, 2 or 3. So typically it should contain 2 bits, but because this is very important information, there's a lot of redundancy added to it. So instead of 2 bits, it's 32 bits long. And furthermore, frequency diversity is exploited, which means this information occurs on the first OFDM symbol always, and it's evenly distributed 4 times, so 4 repetitions in the frequency domain. So this is a very robust control channel. It's very tolerable to interference and can perform even in the very low SINR regime. But we'll see that when you have the macro femto deployment, this SINR tolerance is still violated. Okay, the next one is the PHITCH, as it's called, is the physical hybrid ARQ indicator channel, and all this channel does is it's the E node B telling the UE whether the uplink transmissions were successfully received or not. The structure is very similar to that of the previous control channel that I showed you, except that it has only 3 repetitions, and it can either occur in the first OFDM symbol or across all 3 if they are used for the control channel. And finally, so it can be like this, or it could be like this, spread across the 3 OFDM symbols. And finally, we have the PDCCH, so the physical downlink control channel. And this is basically the E node B telling the UE where it should find its data in the data region. So in this simple example, I have 3 colors, green, blue and red, and the 3 colors represent 3 UEs that could be served by this one E node B. And as you can see, that they appear to be randomly distributed, which is good because then you can use time and frequency diversity. And the UE basically has to decode the information contained in these blocks in order to identify where in the data region its resources can be found. So this was an overview of the 3 control channels that occupy the first 1 to 3 OFDM symbols in LTE. So what does it look like? So I coded the system up and I took a snapshot of the control region, and it looks something like this. So these blue ones are the PHITCH. This is just one small part of the entire frequency spectrum. This is one of the repetitions of the PHITCH. The black ones are the reference symbols. The red ones are PDCCH, assigned to multiple UEs telling them where to look for the information. And here is the PC Fitch, which is also just one of the repetitions. So it goes on like this. This is what the control region looks like. So we focus on the performance of the PC Fitch and the PDCCH in this work. And we do that because the PC fetch is very restricted. It occurs only on the first OFDM symbol. It has 4 repetitions, and if you don't decode the PC fetch, you don't know where the data part of your control channel starts, and you lose the entire subframe. So it's very important that this control channel should work properly. Okay, so this is just another recap of what we can and cannot do. So in this figure, we have the macro layer on top and the femto layer down. And if the femto, so typically the femto layer should be serving much less users than the macro layer. So its control channel should be thinner than that of the macro layer. So I assume here that it's 1 OFDM symbol long, and in the macro layer it's 3 OFDM symbols long. So typically once the control channel ends, the data channel starts, and this should be fully occupied in most of the cases, which means that there's complete interference going from the femto to the macro layers. And this is a very bad situation for the macro UEs that are trapped inside femtocells. What you can do, it's a very simple scheme. You can force the control channel, the control region to be sparse in the femto layer, which means that you can force it to be 3 OFDM symbols long, even though it doesn't need to be. By doing this, you have much more space available to distribute all the control channels, and thereby you can reduce interference caused to the macro layer. And then the most extreme and severe case is where you simply don't transmit anything on the femto layer, and that would reduce the interference, where you still have interference coming from these CRSs. So this is something you can already do without making any changes whatsoever. Okay, so let's look at what the system model looks like. This is the well-known 5x5 3GPP grid model. Each little square in this grid is an apartment. Each apartment may or may not contain a homie node B, and if it contains a homie node B, it will serve 1 user. And then we have macro users distributed uniformly in the system, and based on such a distribution, they may or may not occur close to an active femtocell. So I've highlighted 2 of these users. These users we call trapped macro UEs, and we will focus all our research on, or all our analysis on them. Okay, so we have some simple parameters. The important ones are this. So an apartment has a 10% chance of containing a homie node B, and the homie node B transmits with much lower power than the macro E node B. And we also model walls and wall penetration losses, etc. So what we see is that when we don't do anything, we see a very, very, very poor performance. So this is the performance of the PDCCH, which shows where the UE should look to decode its data information, and the solid curve represents the case where there is no coordination. But when we introduce some interference mitigation schemes, we see that we move quite a bit to the right. This vertical line represents the tolerable SINR. So I've just made it 0 dB. In reality, it's actually a little lower than that, but because the PDCCH can be coded in many different ways, it can be made less or more robust to SINR. So I've just chosen 0 dB. And this case here with the stars is our benchmark system, where we turn off all the femtocells. So we have no interference from the femto layer. So we see that we're still some distance away, but our performance is still much better, definitely, than the case when we do no coordination. I have to point out that in the case of the control channels, it's a binary decision. So either you decode the channel or you don't decode it. It doesn't matter if you have a very high SINR or a very low SINR. It just has to be above the threshold. So it doesn't matter if we are in this region or not. We just have to be higher than this vertical line. So already with these sparseness, for example, or with almost blank subframes, we are doing quite well. And the situation can be somewhat improved if we introduce power control, which is seen on the right hand side. Okay, but of course, as I mentioned, when you do this kind of sparseness or almost blank subframing, you will reduce the data capacity on the femto layer. So that is something that we have acknowledged, but not shown in these curves. So these curves only represent the performance for the trapped macro UEs in the system. Okay, so the story is quite different for the pH, and that's because the location of the pH is different than that of the PDCCH. So here we see that we have an improvement over the no coordination case, but the performance is still not very good. The same holds true when we have power control. And moving on, for the PC Fitch, again we see a very similar story, and that's because the pH and the PC Fitch are located very similarly in the time frequency domains. So the macro performance improves, as we can see. The curves move to the right, but it's not good enough. It's not acceptable. So we have to do something about that. So that was a brief summary of the existing techniques and how they perform. And we have seen that the PC Fitch performance is quite poor, and the PC Fitch actually is the most important control channel, so we should do something about that. So the next section, the next slides will deal only with that. Okay, so other things that are being done to protect the trapped macro UEs. There's what is known as the CSG ID manipulation technique. This can be found in this 3GPP document. What it does is you have a default and a dedicated closed subscriber group ID, and basically when there's a nearby macro UE, the home E node B chooses to change its ID to a dedicated one, and by simply changing the ID, as I'll show you later, you can actually rearrange the configuration of your control channels. But this is not a very clever technique, because the home E node B should be aware of when a macro UE is close to it, and this is quite a non-trivial problem to solve. Also, a central controller would be required to ensure that no home E node B uses one particular CSG ID for a long time. So there's quite a lot of exchange of signals in the system, and this is clearly a non-optimal solution. The other solution would be this physical cell ID reservation. So it's possible that you just save a particular set of the physical cell IDs which can only be used by femtocells. That's okay, but what about the interference coordination? You still can't do anything about that. So these are some of the techniques that are available, that are described in 3GPP documents, but they're not good enough. So what we actually do is we change the physical cell ID of the home E node B at startup, so we don't only choose from a particular subset. We have the entire 504 physical cell IDs to choose from, and we choose them cleverly so that they reduce the collision to the PC Fitch of the trapped macro UEs. So let's look at why the PC Fitch is so important. I've already mentioned that if you cannot decode the PC Fitch, you cannot decode the subframe. The entire subframe is lost. And the good thing about the PC Fitch being looked at is that on the home E node B, we serve a very few number of users, and because of that, we have a lot of flexibility to shift things around in the time and frequency domains. So let's look at the proposal. As I mentioned before, here is the PC Fitch distributed 4 times in the frequency domain, in a cell whose physical cell identity is x. Now x is an integer, so let's increment it by 1. When you increment the physical cell ID by 1, everything moves one resource element lower, or actually 4 resource elements down. And it basically continues to cyclically shift this way as you increment the physical cell IDs. So basically the location of your control channels depends very much on the location of your cell ID. So this is something we're going to exploit. What happens to the PDCCH? As I told you, the PDCCH is distributed pseudo-randomly in across the time and frequency domains. So here is one possible configuration for a cell whose physical cell ID is X, and when you increment it by 1, you get, look at the red ones, you get a completely different distribution. And when you increment it again by 1, the distribution again changes completely at random. Well, it's not random, of course. There are certain equations that tell you how it's distributed, but to the naked eye, it appears to be random. So once again, the PC-Fitch and the PDCCH both appear to be randomized when you change the physical cell ID. So what do we propose? We propose the following. On the femto layer, we should choose a physical cell ID in such a way that the interference caused to the PC-Fitch on the macro layer is either reduced or completely eliminated from that femto cell. So it's quite easy to do this because the femto cell is equipped with a downlink receiver. So all the femto cell needs to do is to sniff the environment and try to identify the physical cell ID of the closest macro E node B. Once it does that, it just adjusts its own physical cell ID so that it doesn't cause collisions for that macro user. There's no signaling required, and it needs to be done only once at startup because macro cells don't move around. So yeah, this is what I said. It identifies the most dominant macro E node B. So once it does that, it decodes the dominant macro E node B's physical cell ID and then adjusts its own physical cell ID to reduce interference. And I've been looking only at the physical, at the PC-Fitch, but we can also do this for all the other control channels, and in addition, we can do this also for the cell reference signals. So we can solve all the problems by simply changing the physical cell ID. What we did in our simulations is we employed the so-called dual stripe model that is used quite oftenly in 3GPP, where you have apartment blocks always appearing in 2 buildings at a time with multiple floors, and again each apartment has a certain probability of containing an active femto cell or not, and we distribute again the macro users uniformly in the system, and thereby they might appear close to an active femto cell. And now we run the simulations. Here's the system. We're using almost blank subframes, and here's the system using our proposed system, our proposed technique. And you will think, okay, so the improvement is not much. It's maybe 2 dB at best. So why are you doing this? It's just extra work for the home E node B. The reason is that when you do almost blank subframes, you actually don't transmit on a certain subframe. No control, no data, nothing. And so if you do this from 10 subframes, if you blank out 2, even 2 in every frame, you still lose 20% of your data capacity. Whereas in this case, you don't not transmit on any of the subframes, you transmit on all of them, and you still improve the performance of the PC-Fitch by a bit. But what is important is that you improve the performance at the lower percentiles, which corresponds to the cell edge throughput, which is very important for LTE.
I think if you did it logarithmically, you would see
even greater.
Very big improvement, particularly below minus.
Sure. Okay, and then of course when you have power control, the situation improves a lot, and in fact we are quite close here to the benchmark, which is the system where you have no interference at all. So the benefits of doing this are quite great, and it's a very, very simple scheme without the requirement for any additional hardware or signaling in the network, etc. Okay, so as I said, the aggressor home node B continues to transmit data, but at the same time continues to reduce interference. This technology is a significant improvement over introducing sparseness, because it incorporates the benefits of sparseness and almost blank subframes. So you reduce interference, but at the same time you can still transmit data, which you can do with sparseness. You can protect many macro UEs at the same time, because typically they would all be connected to the same macro E node B. You need no additional hardware or signaling. It's completely backwards compliant, so the home E node B changing its physical cell ID has no impact on a user's capability to connect to it or not. And you can seamlessly use this with power control to even further improve the performance. So the first study was dedicated to control channel performance in LTE. We looked at only the trapped macro UEs because these are the vulnerable ones. We analyzed some backward compatible techniques. We showed that we have a good improvement for PDCCH, but not for the PC fetch, which is the important one. So we analyzed that further. We came up with a new technique to protect the PC fetch without losing the femto subframes, and we could think of still some further improvements. For example, power consumption analysis, handover improvements, so that you don't have this ping pong of users coming in and out. New control channel designs, etc., etc. Okay, so that terminates part 2, which was femto to macro interference. I hope you're not too bored already, but people in industry, we have to think about this. Okay, now let's look at the case where you have a lot of femtocells very close to each other, causing a lot of interference to one another. So as I mentioned, you have the interference between the femto user and the macro cell, or macro user and the femto cell. But the third case is the important one, which is femto cell to femto user equipment when the femto user is not connected to that femto cell. So how can we maintain an acceptable performance even in dense femtocell networks? That is the question. And the answer lies in this very nice technology provided by LTE-Advanced, which is carrier aggregation. As I mentioned, we have 100 megahertz, and we can have up to 5 component carriers in this. Okay, how should the cake be eaten? How should we divide resources between these users? Let's assume a system where out of 10 apartments, 3 of them are occupied, each one serving one user, and we assume a system where we have 3 component carriers available to us. These red arrows here represent interference. So for example, cell B would interfere with this user from cell C, and so on and so forth. So interference is a severe problem. And as I've already told you, resource partitioning is widely used to enhance the performance of cell edge users. So basically what we can assume is that interfering neighbors should simply transmit, or should simply use different component carriers and not use the ones that they know will cause interference to their neighbors. But what's the drawback? The drawback is if each femtocell uses only one component carrier out of all the available ones, this will significantly reduce the resource efficiency of the network. So you will only be operating at 30% when you could actually be operating at maybe 60 or even 100%. Furthermore, with femtocells, you have vast variations in interference conditions. So a user could move, for example, and then not be interfered by a neighboring femtocell, or a femtocell could be completely turned off and then not exist and not cause interference. So the scheme, any scheme that you come up with has to be adaptable to such conditions. So you cannot simply use schemes that you use in a macro network and just put them to work in a femtocell network. My time is over. Okay. So that's just what I mentioned. So for example, have a look at this user over here. If this user moves, then homie node BA is no longer interfering with that user. So homie node BA should be able to use more resources than before. So this is what I was talking about. You have to be able to come up with a system which is very dynamic. So it should be dynamic in nature. Now let's look at how the resources could be distributed. So cell A could use component carrier 1, B could use 2, C could use 3, and everything's fine. Nobody is causing any interference to anyone. Let's name these as primary component carriers. But what else can we do? We notice that in cell A, we could even use component carrier 3 because we're not causing interference on that component carrier to anybody else. So cell A, instead of operating at 33% efficiency, could actually be operating at 66% efficiency. So we have to come up with a system that does this dynamically. And you could think of it as two approaches. You could have all the femtocells connected to one another via some kind of logical interface, which are then connected via another logical interface to some kind of central controller which does all the processing and tells which femtocell to use which resource. That's very nice because the femtocells then need not have a very high computational capability, but you need to have all these interfaces and you need to have this central entity. You could also do it without the central entity, which would be very attractive because then basically you don't need any additional signaling, or not a lot of additional signaling. So we are going to, in this final part of the presentation, look at both these techniques and see what we can do. And of course, we should operate in the realm of reality, which means that we should operate with what we have, which is LTE-A. Okay, so let's look at the first approach. We look at a central approach where resources are assigned centrally, and they should be more efficient resource utilization than the distributed approach. But we need extra signaling between the base stations and the controller, and a high computational complexity would be needed at the controller. Okay, so let's again look at our toy example. We have 3 femtocells active, causing interference to one another, and we have this central controller. So the question is, how do we assign the subbands? So we could use the UEs. The UEs could assess the interference that they experience in the downlink. For example, this one here sees interference from cells A and from cell C, and it tells it's serving homie node B, I see interference from A and C. And similarly, the same thing could be done in the other cells. The E node Bs collect all this information and they send it across this logical interface, whatever it may be called, to the central controller. So they just tell the central controller which component carriers they see interference on. Or, in other words, which cell they're seeing interference from. So for example, C could tell the central controller that it sees interference from cell A, B from cells A and C, and A from B. The central controller then makes a graph where each node in the graph is a base station, and an edge between two base stations means there's interference between them. So then we could use a very nice graph coloring theory to color the nodes. So what is graph coloring? Just very briefly, without going into any details whatsoever, graph coloring is a way of coloring the vertices of a graph such that no two adjacent vertices share the same color. So this is exactly what's used to color maps of the world, and this problem has been around for a very long time. It's been solved. You need 4 colors. In a graph like this, on the left hand side you have nodes connected to vertices, so you have certain base stations. So as you can see, this is again our classical 5x5 grid model, and you have certain red lines between the triangles. The triangles represent homing node Bs, and the red lines represent interference between them. So for example, between these two homing node Bs there's interference, but between this one and this one there isn't. So if we apply our graph coloring theorem, we might come up with a configuration like this, where colors are assigned to each node in such a way that there is no interference between neighboring nodes. This is great. So we've solved our problem. We've assigned one component carrier to each base station in such a way that there's no interference. But that's the problem. We've only assigned one component carrier. What about the rest of them that we have available? Yeah. Yeah,
isn't this problem NP hard?
It is. But if you just do it numerically, you should be able to come up with something.
Yeah, at least something.
Okay. Alright, so how do we improve upon this?
Can I just say something on this NP hard stuff? A warning to academics. Computers are very powerful these days, and where academics say this is like not possible, you just sit down, let them do a complete search. Takes you, instead of 2 milliseconds, maybe 3 milliseconds, and it's all done. A lot of nodes, how many? 3 billion, 10 billion? To really make it feel, I mean, even with thousands of nodes, you get an exhaustive search very quickly.
But think of the kind of system we're dealing with. We're dealing with a system where we're looking at dense femtocell networks, and a dense femtocell network would occur in a building, in a residential complex, where even 100 is quite a lot already. So in that sense, yes, it is NP hard, but it's exactly.
But million, not sure.
I'll give you a simple example. I mean, it's out of a different community. It's the embedded machine-to-machine stuff on sensor networking, actually. So, our community, academic community, says, you can't have a centralized scheduler for a network of, I don't know, several thousand nodes. Now, Chris Pista from Berkeley didn't know about it, so he did it. Okay, so he has now sensors running with his company Dust Networks, millions of sensors literally on the refineries offshore in California, centralized scheduler, no problem. It might not be the optimum of all, but it just works really, really well. You see, so NP hard is something, for an academic they shy away. Industry, they don't really care. If it works, it works,
Yeah, that's quite an important distinction between academia and industry. It's something I had to learn. Okay. Alright. Once again, toy example. We have nodes A through F, and we've colored each one very cleverly with the 3 available colors we have. And then we could apply our algorithm once again with a different starting point, and we could again color the nodes with different colors such that we still don't violate the interference condition. And by doing so, now each node may or may not have more than one color assigned to it, thereby increasing the efficiency of the system. So, in the simple case where you assign one color to each node, in this example, you could have a resource efficiency of 1/3. And then you could apply graph coloring again, and depending on your starting point, you could have a resource efficiency of 6/15, or if you are more clever about it and you think about where to start from and so on, you could go up to 9/15. So it all depends on how you apply your graph coloring the next time. So for this, we come up with a clever cost function. Once again, I'm not going to go into any details here because otherwise people will just fall asleep. But we have papers published on this, so you can have a look at those. Okay, so how do we do this? In the first step, it's very simple. We apply graph coloring S min times, where S min is the minimum number of component carriers we want to be allocated to each base station. We use for this the cost function to assign one component carrier to every base station in every iteration, using the method I showed on the previous slide, where you carefully select where to start from. And then in the second step, for each component carrier, again use this cost function to identify the combination of base stations which maximizes the utilization of this component carrier. So don't think about slide 10. Slide 10 is clearly wrong. It's on a previous slide. I'll correct this later. Okay, so basically the advantages are what? You have dynamic adaptation according to the prevailing interference conditions. The number of component carriers which are assigned to each base station is automatically adjusted. It's not a fixed number. So if the base station sees less interference, it will be assigned more component carriers and vice versa. So you have a low wastage of resources, and the scheme is, well, not very computationally complex given the size of the problem. So in our simulations, we considered again this 5x5 grid problem, but in this case the occupancy is 100%, which means that each apartment has to contain an active home node B. We looked at downlink only, and we looked at femto-to-femto interference only. So we assume that this is an isolated system, that not embedded in any macro cell. Okay, and then we looked at the performance of the SINR. So the black curve represents the SINR when you have reuse 1, which means everybody uses everything that's available. The blue curve represents the case when you have conventional graph coloring. So you apply graph coloring 6 S min equals 6, so 6 times, given that we have 6 component carriers available. And the red curve represents our system, so where we think of applying graph coloring with this cost function. And we see that when we look at the SINR, actually conventional graph coloring does better. So why not use it? The actual question is, when we look at the CDF of capacity, we hit a wall when we are looking at the conventional graph coloring. So once you when you do conventional graph coloring, you only assign one color to each node, and therefore you simply hit a wall. You cannot exceed the capacity beyond a certain limit. The situation is better when you look at reuse 1, because in reuse 1 you use all the resources you have available at each and every homie node B. And when you use our system, you actually exploit the benefits of both. So you assign resources such that you reduce the interference caused to one another, but at the same time you're not limited by the number of resources that you use. So if we look at the lower percentiles around here, we see that with reuse 1 we have a very, very high outage, almost 30% outage. And this is because when you use reuse 1, everybody is causing interference to everyone else. And some UEs which are at the cell edge will simply not be able to perform at all. The situation, of course, improves in the high percentiles. These represent the cell center UEs. The reason our scheme does so well is because we use graph coloring such that we actively try to reduce the interference caused to other users. And so even cell edge UEs can perform well. And that's the same trend that you see with conventional graph coloring, because what else is graph coloring but reducing interference to your neighbors? But then because we have the ability to use more than one resource per femtocell, we can exceed tremendously the performance of the conventional graph coloring. So basically, we exploit the benefits of both reuse 1 as well as conventional graph coloring, which is very encouraging. And then what we did is we varied the probability that an apartment contains an active femto base station from near to 0 to 1, and we saw, or we analyzed, what percentage of subbands are actually used in the system. So in conventional graph coloring, because you only give one color to each node and you have 6 available nodes, you have, regardless of the activation probability, and a usage ratio of 16% or something like that. But this graph, the red curve, actually shows how dynamic our system is. So when you have very low activation probabilities, you can assign almost all the resources to all the homie node Bs. But as you increase the activation probability, because the interference graph is getting more and more dense, you have to assign less and less resources. So we can see that our system is very adaptable to the interference situation, but at the same time, each base station on average is still being assigned more resources than when you just have conventional graph coloring. So these are some very encouraging results. And finally, we saw the effect of changing the SINR threshold. So I did not explain what this threshold is, so just allow me to go back a little bit. When you construct this interference graph, just a second, where are we? Right here. So when you have an interference graph like this, an edge exists between two nodes when there's interference between them. But how do you determine when there is interference? You use, of course, a threshold, an SINR threshold. So in the results that I showed you, our SINR threshold was 5 dB, and you can even see this from the results that everything begins at 5 dB. So our system is conforming to the limit that we put on it, that the SINR threshold is 5 dB. And the question is, what happens when you change this SINR threshold? So we looked at the 5th and 10th percentile user capacities. So these represent the cell edge user capacities, and at the same time we varied the SINR threshold for constructing our interference graphs. And we noticed quite a nice effect, that if we can choose this SINR threshold cleverly, we can operate in somewhat of an optimum condition where, okay, and this graph is quite complicated. So on the x-axis we have the average user capacity, so per user capacity, and on the y-axis we have the 5th and 10th percentile user capacity. So we want to be as far in the right hand corner as possible. So basically there is something of a sweet spot if you choose your SINR threshold correctly. So this is something we're still investigating, and is definitely a topic of further investigation. Okay, so femto-femto interference is a severe problem in femtocell networks. This is quite clear, especially when the network is dense. So as we saw from the graph where we changed the activation probability, when the network is not dense, it's very simple. You just give all the resources to everyone, and then the system performs well. But when it gets more and more dense, then you have to think about assigning resources cleverly. Coverage holes are reduced when you assign resources dynamically, and when you assign them cleverly, you have a high resource utilization. So we have significant capacity improvements for cell edge UEs at the expense of a modest decrease for cell center UEs. There's always a trade-off, right? No free lunch. So in the next section, what we are going to discuss is the situation A, where we move from a centralized approach to a distributed approach, and B, where instead of serving just one UE, a femtocell might serve more than one UE. So we want to make our lives as hard as possible. So in the distributed approach, the base stations do not consult with any central controller. They make decisions on their own. The system should be less complex, but then we have the situation where the base stations need to talk to one another and tell each other what the interference is, what not to use, what to use. So there's a bit of an extra signaling or high signaling overhead in the system, and it might require a long time to reach a stable situation, because if one base station changes its configuration, the entire interference scenario has changed, and maybe there's a lower resource efficiency than the previous case. Okay, so we want to autonomously assign resources in unplanned wireless networks, which femtocell networks certainly are. And we want to balance the high spatial reuse of radio resources with interference protection for cell edge users, which I've been saying all along. The proposed method relies on user equipment measurement and dynamically adapts to the interference conditions. But even though I said there's more signaling overhead, it still is less than what would happen with existing LTE and LTE-Advanced signaling procedures. So also one important thing is that this can be adapted to work in equally well in the time and frequency domains. Okay, back to our toy example. 3 cells, 3 component carriers. Who gets what? This is the interference situation. These red dashed lines show what's interfering with what. Here we have each cell using one component carrier. You can simply do this by sniffing your environment. As I said before, the home eNode B has a downlink receiver. So just by listening to its environment, it can assign a component carrier which it sees is experiencing the least interference. But then you again want to reach the situation where cell A is using 3 because component carrier 3 is not causing any interference to the other cells. So basically what we need to do is we need to be able to classify each component carrier based on what its use in the cell will be. So let me go into some more details. So we have what we call a reserved component carrier. Reserved component carrier means that it's reserved for the use of a particular cell, and because it's reserved, it's used to serve the cell edge UEs which are the most vulnerable. Okay, so we have in cell A, component carrier 1 is reserved and it serves both these UEs, and in cell B we have 2, cell 3, C we have 3. In relation to reserved component carriers, we have banned component carriers, which means what is reserved for one cell is banned for its neighbor, such that its neighbor has no chance of causing interference to that cell. So this guarantees SINR at the cell edge. And finally what we have is the rest. And the rest we call auxiliary component carriers. So these ones are allocated to UEs facing less interference. So for example, cell center UEs. Neighbors not restricted, which means these component carriers could actually experience more interference than the others. But because we can allocate them in addition to these reserved component carriers, we increase the reuse efficiency. So in this example, component carrier 3 is auxiliary and can be used in cell A because it's being assigned to this UE, and this UE can cope with additional interference because it's not seeing any interference from neighboring base stations. Okay, so what is needed to get this to work? We need the IDs of the interfering base stations. So in LTE, we have what is known as RSRP, receive signal strength R, receive signal strength, receive power, right? So basically it's just the received power of the reference signals from the neighboring cells. And this can be easily done by every user equipment, and it just needs to report back to the base station which base station is causing interference above a certain threshold. So for example, in this case, the green UE will report back to cell A that it's seeing interference on component carriers 2 and 3. And in this case, it's seeing interference on component carriers 1 and 3. So this information is fed back to the base stations. The base stations are assumed to be connected to one another via some kind of logical interface, such as the X2 interface, which I told you a long time ago about. So basically, this means that A is going to tell its neighbors B and C not to use component carrier 1. Similarly, B will tell A and C not to use component carrier 2. So these are the reserved component carriers. So now we've already reached a situation like this. And finally, we measure the SINR over each component carrier. This is also done at the UE, and it just uses existing LTE signals. So again, we use this RSRP. We can also use received signal strength quality, RSRQ. There are lots of things we can use to measure this. And basically, the reason for doing this is we find out which component carriers are available for transmission as either a reserve component carrier or an auxiliary component carrier. And for this, we create something very simple. So for example, we have the columns 1, 2, and 3 representing the component carriers, and each UE states whether it receives an SINR above the threshold or not on that component carrier. So for example, the green UE sees a good SINR on component carrier 1 and not such a good SINR on the others. The blue one sees, because the blue one is here, not surrounded by any base station, it sees a good SINR on all the component carriers. Similarly, in cell B, the UE sees only good SINR on component carrier 2, and in this cell, similar to this blue UE, there's good conditions on all the component carriers. But in cell A, 2 is banned. In cell B, 1 is banned, and in cell C, 1 and 2 are both banned. So basically, this means that the green UE will be assigned resources from component carrier 1, the blue UE will be assigned resources from 1 and 3, and so on. So it's all very simple. We just have to report back to the base station where the good SINRs lie. And eventually we should end up with a situation like this. There's a question?
Yes. Are you assuming therefore that the user equipment are able to do their measurement and then be synchronized to every
I mean, this is
fab in the neighborhood.
Yeah, this is anyway done in LTE. You know, the UE needs to make measurements of neighbors in order to notify the cell whether handover is required or not. This is continuously done by the UE. So we're just using this methodology to help us with our particular situation of interference management.
So this is done on every band.
Yeah, this is done on every band. Okay, so now I'm really close to the end of my talk, so you can start waking up on the count of 3. We come to our last acronym. As you know, we all really love acronyms. This one is called DACA, Dynamic Autonomous Component Carrier Assignment, and the scheme is very simple. So the UE makes the measurement, it receives the SINR and the identity of its interfering base station, and it feeds that back to its serving base station. The serving base station at the same time receives an indicator from its neighbors saying do not use this component carrier. Then it basically recomputes its component carrier assignment, does the resource allocation, which uses the PDCCH, which I told you about, and finally sends a reserve component carrier indication to its neighbors. So that's how the process looks. This is event triggered, so the component carrier configuration is updated only if there's a change in the interference environment. So it's not done on a millisecond basis, but maybe on the basis of a few seconds, on the time scale of a few seconds. All base stations are synchronized with a time duration equal to that of a time slot, and between 2 time slots the configuration remains static. Okay, so again we use our 5x5 grid model and we compare our system to what we call base station sniffing, which means the base station listens to its environment and chooses the best 1 or 2 component carriers that it can see. And of course we compare this with DACA, and we use an SINR threshold of 5 dB. Okay, we see some very interesting results once again. So with base station sniffing 1 out of 4, we see the best SINR performance. But as usual, you know not to be deceived by this, because this will not translate to higher capacities. With base station sniffing 1/2, so 2 out of 4, of course the SINR performance is reduced. But we see already some very nice gains with our system, which means that all the UEs are getting a better than 5 dB performance. So this is very encouraging already. And when we look at the user capacity, we see that at the cell edge, which is in this low percentile regime, we have a very good performance improvement over the other 2 systems. And even at the high percentile regime, we still have a very good improvement over the other systems. And that's quite clear, because in the case of the the red curve, where we use only 1/4 of the resources, we can only achieve 1/4 of the total capacity. Over here we can only achieve 1/2 of the capacity, but here we can achieve much more than that, because we dynamically assign the resources. And the reason the curves are stepped is because there should be 6 steps, 1, 2, 3, 4, sorry, depending on the amount of component carriers we use. So basically when you use only 1 component carrier, this is the highest capacity you can reach, because we use truncated Shannon bound model. And when you use 2 component carriers, this is how the capacity you can reach, 3, 4 and 5. Okay, and then we looked on the x-axis at the mean cell capacity and on the y-axis at the user capacity. Again, the aim is to be in the top right hand corner. And what we see is that with our proposed system at all percentiles, so at the cell edge and even towards the cell center, we have better performance than the other two systems. So this approach, even though it's distributed, still exhibits a much better performance than the static systems. And finally, as I mentioned, we see that I told you that we need some time to stabilize the system, and this is what we see when you look at the time slot. So we simulate 10 time slots, and we look at the percentage of assigned resources and the percentage of collisions where the SINR on component carriers is very low. And we see that we start off with 25%, which is quite clear because in the first iteration you only assign 1 out of 4 subbands, component carriers to a cell, and then in the next iteration you know a bit more about the interference conditions, so you assign more resources, but then you start causing interference, so then you reduce the amount of resources, but then by the third step you're already quite at a stable state. So you have more collisions in the second time slot, but then you sort of stabilize already out after 3 time slots. So this is quite good performance. So you just need 3 iterations really to have a stable system until your interference conditions change. And finally, as I mentioned, there's again a sweet spot which you can operate on when you cleverly assign your SINR threshold for that particular scenario. Okay, so I just want to wrap up now because I think I'm already out of time. We have looked at some fairly simple and backward compatible femto-macro interference techniques, mitigation techniques. We've identified that the control channel is very, very susceptible to interference. We, in particular, identified the most important control channel to be susceptible to interference the most. We addressed this problem by looking at a clever interference mitigation technique. We then considered the case of femto-to-femto interference. We looked at some other interference mitigation techniques which rely on central controllers and which rely on distributed approaches. So, finally, where do we go from here? As you all know, there's always avenues of further research. So femtocells are here to stay, that's one thing. What we could do in next releases is actually design air interfaces that take into account that femtocells exist, rather than just work with existing macrocell interfaces. I know that lots of people are doing research on that. New ways of dealing with handovers, because you have low power nodes embedded in high power nodes. So the handover issue is not that straightforward anymore. We could look at scheduling problems with tight macro to femto cooperation, femtocells with cognitive radio, who knows, MIMO techniques, etc., etc. And that concludes my talk. So thank you very much.
Thanks a lot for the talk. Any questions? I have a question on the interference, the evolution of, let's say, how we see the interference. I mean, wireless LAN also, we were very worried that in the ISM band, wireless LAN would be interfered with the microwave and the other way around with Bluetooth devices and all that. And, all these papers start to disappear, and now everybody worries about wireless LAN to wireless LAN interference. Do you think the same will happen maybe with the femtocells as well, that the main worry that we may interfere into macrocells the other way around will just be such a small problem compared to the femto-femto?
I don't know, it's quite a tough problem to actually analyze. Unless we have a lot of femtocells, it's very tough to actually characterize the problem, because we use very simple models here where each wall is 20 dB or 5 dB loss, and it's the models that we deal with are very simple, and indoor propagation is much more complicated than that. So if we use this one frequency reuse of 1, I'm quite sure there'll be a problem eventually. But if we already start migrating towards more clever
like you have presented,
techniques, then maybe it won't be a problem. I don't know. It's hard to say.
All right. So if there are no other questions, oh, there's a question down there. Yeah.
So I have a question regarding the last algorithm for the convergence. Does this algorithm converge under all scenarios, or there are like kind of scenarios where your algorithm will not converge?
So as far as I know, it converges under all the scenarios we looked at. But of course, the universe contains a lot more scenarios, so I'm not sure. Depending, maybe if we change the distribution model, the performance might be different. But I think eventually it will always converge, because it's taking feedback from the UEs. So there is a loop over there which makes sure that the algorithm reacts to the interference environment. So maybe it will take longer to converge, but I have a feeling that it will always converge.
Thank you.
Okay, if there are no other questions, then thank you very much, Zubin.
Oh yeah, absolutely.
Excellent.
Yeah.
That's very good.